Hello, everyone. Today, I will introduce security and performance in the delegated user-level virtualization, which I finished with Dingji Li, Zeyu Mi, and other mates of iPads Lab. And I'm Jiahao Chen from iPads Lab of Shanghai Jiao Tong University. Virtualization has undergone 3 stages, gradually moving the functions outside of the kernel mode. In the first stage, all functions were implemented in kernel mode to multiplex the scarce resource. In the second stage, they offloaded functions to the host OS, user-level helpers, or management VMs. However, some functions are still stuck in the kernel mode, like memory virtualization. The third stage began with the release of hardware virtualization extensions like Intel VMX. This further reduced the kernel involvement by shifting more virtualization functions to the hardware. Nowadays, the third stage hypervisor usually takes a split module, which consists of an in-kernel driver and a user-level helper, like a QEMU KVM. Compared to the user-level helper, vulnerabilities from the in-kernel hypervisor components cause significantly more risks to the host kernel, for they are higher privilege and they interact most frequently and directly with guests. Unfortunately, there are about 500 in-kernel CVEs from KVM and Zang, and most of them can cause the host kernel to be attacked by guest VMs. The attack effects are also severe. Over 90% of the host attacking CVEs can be exploited to launch DOS attacks, which can compromise the reliability. And the attack effects are also severe. Over 90% of the host attacking CVEs can be exploited to launch DOS attacks, which can compromise the reliability of the entire system. Part of them can even enable attackers to escalate the privilege and compromise the host kernel. Finally, such CVEs can be exploited at relatively low costs by experts. Prior works have tried to deprivilege the in-kernel hypervisor components to eliminate the CVEs, like Nova and DHype, so that the vulnerabilities can be deprivileged to the user mode along with their components. However, prior works cannot eliminate all the in-kernel CVEs. To find out why, we identified all the components the KVM CVEs are located, and further divide them into VM plane and hypervisor plane. VM plane means the components that serve VMs directly. Hypervisor plane means the components that serve the VM plane for hypervisor control. And we found that all the host attacking CVEs reside in the VM plane. The prior works can only remove part of the VM plane components, and this results in 47 of the 80 host attacking CVEs on KVM are left in the kernel. This is because the in-kernel components they left must perform some privileged operations to work, so they cannot be moved to the user mode. On the other hand, moving most of the kernel components to user space will result in more expensive mode switchings. This table shows the overhead of an MMIO read operation in QEMU KVM on different architectures. And from the breakdown, we can see that about 44 to 73% of the overhead are consumed by the additional forwarding on different architectures. So simply moving more kernel functions to user space can cause significant overhead. We identified that the tight coupling between the hardware virtualization extensions and the kernel mode is the root cause of these problems. So here is our solution. We propose delegated virtualization to safeguard the security and the reliability of virtualization systems. Its architecture has 3 components: the delegated virtualization extension, or DV extension for short, the divisor hypervisor serving each VM directly in user mode as the VM plane. And we also have a tiny DV driver in the kernel as the hypervisor plane without vulnerabilities. Our threat model is that a malicious tenant can compromise the hypervisor and try to further attack the host kernel and other VMs. And in our design, the host kernel should be safe even after the hypervisor has been compromised. We assume that the hardware is correctly implemented, and the host kernel with DV driver is trusted as well. We propose DV extension for the hardware. It lifts the virtualization interfaces securely from the host kernel to the user mode. Through these interfaces, user-level process can access VM information and control VM behaviors. It also provides delegatable VM exits, which enables the VM to directly traps to the user mode. Based on DV extension, we can further build Divisor, the user-level hypervisor. For traditional hypervisors, all VM exits are trapped to the host kernel, but this is not the case in Divisor. All guest exceptions that result in VM exits are trapped to the user-level hypervisor. Then it can get the trap information via the user-level virtualization registers and handles it without any kernel involvement. Finally, Divisor returns to the guest directly. Divisor directly handles stage 2 page faults and configures the stage 2 page table in user space. However, a compromised Divisor may allow its VM to access the host kernel memory by directly mapping the attacker's GPA to an HPA of the host kernel. We use physical memory checking, or PMC for short, to limit the physical memory range that VMs can access. As shown in the picture, DV driver will set up the PMC so that the VM will trigger a fault if the HPA it can access is beyond the range allowed. We implemented Divisor's prototype on the RISC-V Rocket chip with this configuration. DV extension does not require expensive hardware modifications because most of its interfaces can be implemented by reusing an extension and hypervisor extension of RISC-V. Actually, only 3 registers need to be built from scratch, and the DV extension only takes about 500 lines of chisel. Divisor consists of about 7,000 lines of code, including about 5,000 for Rust and 2,000 for C and assembly. A tiny kernel module works as the DV driver, and it only has 337 lines of code. Let's talk about the security. A malicious VM can exploit hypervisor's vulnerabilities to compromise the entire system. However, Divisor has removed all these vulnerabilities to user mode. Therefore, the guests cannot harm the host kernel directly anymore. Although Divisor is developed in Rust with memory and thread safety, all thread models still allow the compromised Divisor. But the attacker is still constrained in a user-level process with no direct threats to other VMs or the host kernel. Finally, lots of existing techniques can be applied to protect the host kernel from the compromised Divisor. For example, Divisor only needs 17 system cores to serve a Linux VM at runtime. Therefore, the host kernel can use seccomp to effectively constrain the attacker. On the other hand, neither the DV driver nor the DV extension provide extra ways to compromise the host kernel for their little code base, and they leak no kernel information or behaviors to user mode. So we can see that Divisor can protect the host system from malicious guests. We performed the performance evaluation on the circuit-accurate file system platform with 2 FPGA boards. Each FPGA runs on an 8-core RISC-V processor with hypervisor extension and a DV extension. We use OpenSPI as the firmware and the Linux as the host and the guest kernel. Our baseline is QEMU KVM. Here are macro benchmarks. Lower overhead is better. For hypercore and stage 2 page fault handling, Divisor consumes 65 and 89% less time than KVM. This is because Divisor in user space need not to perform operations that are only necessary in the kernel, and choose a dedicated but more conscious way. For MMIO emulation, divisor is 10 times faster than KVM due to the shorter path without extra forwarding. For the virtual interrupts, we also optimized the KVM with the post-header interrupt provided by DV extension. So both KVM and divisor's guests can issue the virtual interrupts without VM exits, so they are equally fast. So we can see that divisor greatly accelerates the VM operations. In application benchmarks, divisor's performance is comparable to the optimized KVM and the native machine on most applications except for memcached. However, we compare KVM with native on other architectures and get similar results. So from the results, we can see that divisor's performance is comparable to the optimized KVM and very close to the native. In summary, we proposed delegated user-level virtualization. It's a new direction for secure virtualization research and development. In this new architecture, the DV extension securely exposes hardware interfaces to user space, and the divisor, the user-level hypervisor, directly serves VM in user space. Our evaluation shows that divisor can protect the host system and the VMs without performance reduction. This project is available on GitHub. Besides FileSim, we also provide the QMU platform to help you quickly start. More details can be found in our paper. Thank you for listening.